Next speaker is Josef Urban, one of the leads of his project focused on AI and reasoning. He is linking in his efforts machine learning with reasoning. That's quite novel approach and unique, pioneering. So I don't want to talk anymore. It's his turn and his time to explain what was done. Thank you very much.
Thank you. So thanks everybody for coming here. I'm Josef Urban, and I've been working here now for let me think 7-8 years. I initially came with an ERC consolidator grant, and somehow Professor Mařík implicated me into even a larger grant. So at some point I was doing two big grants together. Luckily, there was sort of an overlapping theme there. And I should say a lot of what I will speak about has already been sort of introduced by Holger Hos's talk. Basically for 25 years, I have tried to combine two areas of what I think forms like human or scientific thinking, and that's learning and deduction. And to start this with a funny slide, I hope you can read this a bit. So if nothing else you remember from this talk, remember this book, Logicomics, An Epic Search for Truth by Alexis Doxiadis, which is an amazing comics book written some 10, maybe more years ago now, about the life of Bertrand Russell and about the basically creation, about like a major revolution in science and mathematics, which many people do not understand. Even mathematicians sometimes do not understand it. So there was this guy called Leibniz. I'm not sure if Holger mentioned him or not. I think so. Who had a very crazy dream. Apart from doing amazing things like inventing calculus together with Newton, that one day humans who disagree, be it philosophers, be it economists, be it lawyers, be it mathematicians, be it physicists, be it computer scientists, will be able to resolve their disagreement by calculation, computation. Computation wasn't defined then. Like they knew how to calculate some things. He was the co-creator of calculus at the time. But he had this crazy vision that one day we will have like perfect computational means to decide major questions, disputes, etc. And this thing, so Bertrand Russell is a great logician and philosopher who participated in this revolution basically in the beginning of the 20th century, where people basically embedded mathematics and by extension physics and hard sciences that are modeled by mathematics into logic. And they didn't know yet that symbolic logic will be the sort of substrate from which computation will emerge. What you today call computers are symbolic logic machines. So many of you are younger than me, have been born to computers. It's like phones, and normal thing for many of you. But whenever you are playing with your phone, doing something on your computer, you are doing symbolic logic. So this in this particular picture from the book, Russell is saying, like, what does it mean that like he dreamt the Leibniz's dream and he didn't achieve it? Well, what he means there is that, like, during his lifetime, we really didn't get there. Like, we started to play with computers, and we sort of barely, by the time he died, started to do mathematics on computers, really reasonably advanced mathematics. But we haven't really moved to the more advanced territories like physics that Holger mentioned, and to say nothing about like law, about legal reasoning, which Adam is sort of aiming for with like various ontologies, etc. But it's a dream, and this dream is sort of coming. I think it's sort of unavoidable at this moment. With all the technology that we have, you may think that AI is giving us now with the chat GPT, etc., the sort of bad side, like the confusing side, like it can do very confused quote-unquote reasoning, which isn't reasoning by any reasonable metric. But like with all these technologies that we have, it seems that like computational mathematics, like proving hard mathematical theorems, is really getting achievable at this point. With that is achievable like all the like, let's say, physics and computer science, which relies on mathematics. And I think what is even achievable, even though that will be harder because it's not exactly a hard science, is really very precise logical layer for things like legal reasoning or ethical reasoning. I think the technology is really getting there. So this project was, to a large extent, about this, about sort of trying to combine the two areas of, let's say, human thinking on computers, to sort of develop technologies that help, that sort of help the human or machine reasoners to find a way, to find the proofs, to find justifications by combining them with the intuition that you can learn, that you can learn when you solve some problems and you learn from those solutions, etc. So that's, in a nutshell, the project was sort of bigger than that. So there were quite a few people. There were seniors, juniors, administrators, affiliated researchers, partner institutions in the Netherlands and in Austria, our valued contacts there, and probably over 40 visitors, like over this time. You can try to see yourself here or see your colleagues there. These are our valued team members. And this is just a plain listing of all the visitors, which, if you know something about the field of automated theorem proving and interactive theorem proving, you will definitely recognize the names, let's say all of the names, at least on the first 3 to 4 lines. Like really, we managed to get here almost everybody who means something in the field of automated theorem proving and interactive theorem proving. So that's already was really amazing to have this possibility to invite these people here and do research with them. The topics was, as I mentioned, like my core area is combinations of like deduction, automated proving with machine learning, With that, a very interesting topic which we basically started and which is today being taken up by researchers around the world and at AI companies like Google and OpenAI and Facebook is automated formalization, which basically means that you take a piece of informally written mathematics, like mathematics written in LaTeX or Word or whatever, and now you train some machine learning system to translate that piece of informal natural language text into a formal text, which you can fully formally verify by computers. So the computer, after the translation to this formal language, I'll show you some example later, can really say that the sort of translated version of this particular argument is logically correct. This is, especially today with large language models or even small language models, and their combinations with various like feedback loops that are doing type checking and semantic checking. This is like a very promising area of research where it looks like instead of what people have been doing so far in the field of verification of mathematics, which is like typing manually a mathematical statement in some sort of programming language and then trying to manually prove it, we may have a shot at basically taking, let's say, all of the mathematics which is out there, which is like in various textbooks or articles, papers, etc., run some sort of reasonably augmented learning / type checking / semantic technology that we train in some feedback loop. And for free or for much lower effort than these humans are currently doing, basically translate some non-trivial part of all these big mathematical texts. And that basically leads to this Leibniz dream that I just mentioned. Like suddenly, instead of, let's say, mathematicians or physicists or computer scientists quarreling whether some proof is correct or incorrect, how to formalize it and how the actually proof steps work, you will have a technology that will do this automatically or semi-automatically for you, like completely, like verifying, like even like complicated reasonings automatically. And again, like for those people who think that large language models are some sort of doom that will bring confusion to the masses, I think this may be one of the cures. Like the fact that you will take, let's say you ask some reasonable question, which is at least slightly scientific, like how would I solve this, let's say, mathematical problem or physics problem, and the large language model replies to in some way. It may be making things up, it may be correct, but if you manage to translate it to a strictly logical form, you may have a shot at basically verifying the answer of the large language model logically, like step by step. And if there is a problem, like the logic verification systems are good enough to tell you today, like here is a logical gap. I don't see how this step follows from this steps. So that's like a very, very interesting area of research that we started. There is more, like there are reasoning areas, like Adam Pease is working on ontologies. Mikoláš Janota, who will be speaking later, works on satisfiability model theories. We have people working on complex systems and artificial life. We have people working on theory of systems and automatic control, data science, operations research, optimization, scheduling and real-time systems, Zdeněk Hanzálek and his colleagues, human-computer interaction, natural language processing, sign language processing, and some more. So the project was big. It was many people working for 6 years, and it produced over 100 papers, where more than 50% of those were with international co-authors. I'll just give you some highlights, and then I will go into what I sort of understand most, which are like these combinations of machine learning and automated deduction. So the project was divided into 3 work packages. The first one was mostly about like these combinations of learning and proving, where basically the main result, which I will show you later, is that we have shown that it is possible to take the best automated theorem proving systems today, which are extremely well engineered, fast symbolic systems, and make them much better by augmenting them with machine learning methods and introducing some sort of feedback loops where the machine learner gets better as the theorem prover proves more problems, and the theorem prover gets better as the machine learner, which is sort of advising the theorem prover, gets stronger by training on these more and more advanced proofs. So it sounds easy and maybe simple today, but basically the main breakthrough we only did 4 years ago. Like before that, it wasn't very clear whether we have something or not. As I mentioned, we did the first systems for automated formalization, and also for things like automated proposing of mathematical conjectures and synthesizing various interesting mathematical objects. We have one, especially Martin Suda, who will be talking later, some victories in automated theorem proving competitions. Our valued affiliated researcher, Bob Verov, who is emeritus at the University of New Mexico and affiliated researcher here, has actually proved some open conjectures producing very, very non-trivial proofs here at CIIRC on our machines, basically, that really like resolve some problems that are interesting for mathematicians. So that's work package 1. Work package 2 was headed by Zdeněk Hanzálek, who is working on scheduling problems. So their results are in mixed criticality scheduling, and for example, they optimize robotic cells, or they are really applied to the level of being able to drive autonomously these small cars, these formulas that actually have their own racing competitions that they are capable of winning. And then there was research by Professor Svítek and his colleagues doing AI for smart cities, which I think has taken off like independently. There's more funding for it now here. In work package 3, we had Professor Kučera, who is like one of the best Czech scientists, who was just recently awarded the Česká hlava, the Czech mind, for solving long-standing open problems in control theory. And then we had people from Plzeň, from Pilsen, doing work on linguistics and sign linguistics, and, for example, winning competitions in hand pose estimation, etc., etc. So the group where Tomáš Mikolov works started very interesting research in complex systems, and I guess we all hope that Tomáš will get the opportunity to continue this research because it's what he is passionate about. So that was a brief summary of the project, and I have 10 minutes to go a bit deeper, and I do not know how much time I will have for that. So I guess some of you may recognize these pictures. So yesterday we walked to the concert with one famous AI researcher, one famous philosopher, like his name is Ed Zalta, that's this guy, and he just left today, and one famous ontologist who is over there, Adam Pease. And it was a funny walk, because as you go through Prague, you see places where people like Tycho de Brahe and Johannes Kepler worked. And I don't know how many of you know this history, but basically, like when these people worked here in 1600s, to some extent, to a non-trivial extent, they started a process that is called the scientific revolution, the basically development of scientific method, which at some point, if you sort of follow the line, went through people like Galileo and Newton and Leibniz, to development of science, to development of natural philosophy, to development of physics, to development of other sciences, sciences like symbolic logic, and as I said, also to development of computers and to development of artificial intelligence. So at that time, I don't know if I have the slide here. No. I think the funny thing is that at that time, there was such a concentration of smart people doing things in Prague that they were thinking that this could be some sort of singularity, something that people would call singularity today, that the world will radically change. And it changed. It didn't change so quickly. There started a 30 Years' War, and that sort of slowed down things a lot. But like it got to people like Newton and Leibniz, who, as I said, like they developed physics, and they all declared all these crazy ideas about computation, which materialized. Like it took some centuries with like symbolic computation. Maybe unfortunately because Babbage wasn't funded as soon as he should have, but it basically happened, and to some extent it started by people like Brahe and Kepler doing what we call today science, doing analysis of data, proposing conjectures, doing computation with the proposed conjectures, verifying whether the proposed conjectures work, refuting them, modifying them, and iterating this process. And this is the process that we today, in my project, want to emulate on computers. It's the process of scientific method, the process of doing science, basically. And I think if we manage to automate it, like their visions might come true, like the vision of computers automatically doing superhuman physics or superhuman computer science is really crazy. Like none of us can think what will happen when machines will start to develop new laws of physics, for example. So I'll move on a bit, because I'm 5 minutes down to the countdown. So I have already explained quite a bit of this. Like what we are aiming at is development of methods that combine the inductive thinking, which is like learning from examples, proposing explanations, conjectures, etc., and basically some sort of deduction, reasoning, computation, and designing the mechanisms which human scientists have in their minds. But somehow we don't really have yet systems that would be as good as human scientists in many. So a very good environment for doing this research is actually mathematics, and in particular computer mathematics, because in other fields it's really hard to see when an idea is right or wrong. You need a human who will sit there for a long time, stare at some ChatGPT output, and wonder whether this is a good product, whether it's a good mathematical argument or good physical argument, etc., or not. In this particular slightly unusual field of computerized mathematics, you get this basically for free. So people in the past several decades have basically managed, by quite a lot of manual effort, but also by some automation, to, let's say, formally express and formally verify a lot of non-trivial mathematics. I may show you some examples. But also like really verify pieces of code, etc., like coding libraries. So this is another picture from that funny book that I advertised. This effort of putting mathematics on this like solid symbolic computational foundation wasn't without problems. So even in mathematics, there were big people like Hilbert versus Poincaré, who had different opinions about it. Like some of them were more in the sort of deduction, the deduction direction, and some of them were protesting, saying that like if you mechanize mathematics, it will kill in the, like the intuition that mathematicians are working with. So this was actually a non-trivial process. But it happened. Like it, in the last century, after like this invention of symbolic logic, invention of computers, starting to develop AI, which, by the way, started with automated theorem provers called logic theories by Newell and Simon. People started to formalize mathematics on computers, develop automated and interactive theorem provers, and do things with them. And you will hear a bit more from Martin and Mikuláš. And this technology is today already useful. So people have verified graduate books in mathematics in these large projects. They have verified serious compilers, like C compilers, operating system microkernels, hardware chips, transport, finance systems, cryptographic protocols, etc. And there are all these crazy visions that start with Leibniz, etc. I'll just quickly, I'm running out of time, show you one example of formal mathematics. So this is a proof that every student of mathematics has at some point seen. It's the irrationality of the square root of 2. And this is how it looks in a formal proof language. This is what you do to have that piece of text that is here formally checked by a computer, by a machine, basically. So that's what these people are doing. What we are doing is to do these things automatically. We do not want to write them manually. We sort of try to prove them automatically. This is an example of one of the bigger projects called the Kepler conjecture. I started to talk about Kepler. So there is a story about him walking across the Charles Bridge in 1610 and being hit by a snowflake. And as he was hit, he started to wonder how, like why the snowflake has a hexagonal shape. And he wrote a treatise about it. And in that treatise, he conjectured that the most compact way of stacking balls of the same size is this sort of orange pyramid. So this stayed open, unproved for 400 years. Then it was proved in like 1998, but the mathematicians didn't believe the proof. So what the authors of the proof did was to formally verify this long mathematical proofs on computers that gave them something like 20,000 lemmas of this sort of shape, which took immense amount of time. But what we could show like 9 years ago is that you can basically automate a lot of that stuff by doing some combinations of machine learning and automated theorem proving. So that was like the first plausible sign that things could be done. How much more can I talk? 2 seconds? All right. So I'll skip this. These are like technical details. Then showing you can probably download the slides later. Showing you what are all the things that you can do when you combine learning and reasoning. These are demos. Again, you can click on them. And these are the products that we have been creating during the 6 years of the project. This is one of our main systems which really broke the ground in the sense that it improved on the best automated theorem provers in the field. And I will not go into it here. What I will just say is that on this slide, you can see one of these feedback loops between learning and reasoning. You start with a system which is not trained, and you run it to solve some problems, and you learn from the solutions. Then you run the trained system again, and it solves some more problems, and then you learn from it again. If you repeat this 6 times, the system improves by some 70%. This is the kind of proofs that we can get today. We can get this one in 4 minutes. It looks like this if you write it manually. And this is some sort of statistics about it. We have done other things, and I wanted to show this to Holger, but I will show him offline. This is a system to which you can give an integer sequence, and it's also running this feedback loop between like verification and invention using actual language models today. And I will skip the language and the Monte Carlo. Basically, what you give it is a sequence of integers, like primes in this case, and it will spit out a program that is trying to capture the sequence. Like in this case, these are pseudo primes. And it can do it in different ways. And sometimes, when you have 2 different ways how the system thinks that it expresses some pattern, like primes, for example, you can ask the question, can I prove that these 2 things are actually the same? Can I prove that these 2 programs are the same? And actually, in some cases, and Mikuláš Anota will be talking about it, we can do it. So this is a SMT problem encoding the equality of the 2 programs. And this is a proof that Martin can produce with the vampire system of that particular equality. Here are some bets that I did actually in 2014, like how far and how quickly this field will move, and I will not linger on that. And let me just thank CIIRC and in particular Professor Mařík for welcoming us all here. Let me thank our sponsors, in particular the European Structural Funds and the OPVVV projects, my valued team members who were all great to work with, our international partners who helped us a lot, the visitors, and most of all, I would like to thank all the international, or the people, not just international ones, but the people who returned to Czech Republic and sort of took this risk of coming from, I don't know, Austria or the Netherlands, etc., and actually survived here, and I think started one of the first really like international English-speaking groups at the Czech Technical University. So thanks a lot. That's it.
Thank you very much. I have to say thank you for organizing such a group, for staying with us, and for promoting the Czech science across Europe. We are a little bit, thank you very much also for the presentation.